Welcome back. Today we are going to discuss work done by a variable force. In previous lectures we have discussed work done by a constant force, what is work, its units. Today in this lecture we will discuss about work done by a variable force. First of all, we see that what is variable force. A force which does not remain constant throughout a work done, which means that if we do work from one point to another point, and during this distance, during this work, force does not remain constant, that is called variable force. So you see that in many cases the force does not remain constant during a process of doing work. For example, a rocket moves away from the earth, work is done against the force of gravity, which varies inverse square of the distance of the earth. As we can see in this example, that work does not remain constant. As rocket goes higher and higher, force acting on it also changes due to inverse square distance. This is also called inverse square law. The center of force decreases and does not remain constant. Force exerted by a spring increases with the amount of stretch pulling, so the force does not remain constant. In the second example, when we push a spring, we see that when we are going to pull it more and more, for this we have to spend more force. So during this work done, force does not remain constant. While considering a work done, we know that what is work? Work is equal to Ft cos theta, or W is equal to Fx cos theta. Fx is horizontal component of the force for measuring of the work. We suppose that force is constant throughout the displacement d. We suppose that the force remains constant throughout displacement or some distance d. For this is better that we can solve it through a graph. We shall now consider the work done by a force which does not remain constant, and we will now consider what is the work done in which force does not remain constant. The work done by varying force can be determined graphically. We will determine it, we can solve it by graphical way. So to do so, we plot a force Fx along a distance d. Seen in this graph, it is a distance from A to B in which work is done, and throughout the distance the work does not remain constant, and it is represented by this graph. In the graph, dA is the dash displacement, dB is the dash displacement in which force does not remain constant. We see that in graph that we have resolved this distance into some particular parts or particular areas in which we suppose that the force will remain constant. Then we will calculate the work done on each part, then we add that will be the sum of the if we sum that work done by these forces, it will be the total work done. So we see that we divide the segment del d into small segments. For example, for segment we indicate the average force by horizontal line dash line. So that is the force. We see that throughout this small distance the average force remains constant. Then work done on each segment, So the work done on each segment will be equal to Fx del dot and del D, where the area of a rectangle del D wide and fx is the fx height as shown in figure 4.5. So this is the main figure. The total work done of the object is equal to total distance will be equal to dv minus dA is the sum of the areas of rectangles as shown 5 in cases 1, 2, 3, 4 and 5. And the average force value of force Fx will be, each segment must be estimated and responsible approximation of the work done can be made. So in this way we can calculate the work done. If we divide the distance into many more segments, del D can be made smaller and our estimation of a work done would be more accurate. If we divide the work into more smaller parts, in these smaller parts force will be constant and we can calculate it more accurately. We see that the path of a body in XY plane as it moves from A to B. And first one, the method in which we calculated by graph, and the now we will see that we can also calculate it area under the curve. We divide the whole segment into a number of small displacements del D1, del D2 to del D and respectively, and corresponding forces are F1, F2, F3 and Fx and R. Total work done will be equal to the sum of all work done in small parts, which is W is equal to W1, W2, W3, W4 and Wn. W is equal to Fx1 cos theta del D1, W2 is equal to Fx2 cos theta 2 del D2, and this summation will be equal to the summation iota is equal to I is equal to 1 Fxi cos Qi del Di. In this limit del D approaches to 0, we have discussed it in earlier lectures. When del D approaches to 0, the total of area of many narrow rectangles equal to the area under the curve. When we made these parts more and more smaller, then del D approaches to 0. Del D approaches to 0 means it is very small. So due to small, the value of force on these areas will be accurate, and this area will be equal to the area under the curve as shown in figure. That is, the work done by variable force in moving the object between 2 points is equal to the area under the curve Fx versus del D, which is equal to del T approaches to 0 summation I is equal to n Fxi cos theta I del Di. In this way we can calculate the total work done by variable force. Let's summarize it. First we will consider distance through which force applied, then we will divide the distance or displacement into many equal parts in which force remains constant in these parts. We will calculate the work done on these parts, then we will sum it. The summation of these work done will be equal to the area work done by the total work done by the body during this displacement. I hope you may like it. Thank you for watching.